Welcome back to the Deep Dive. We're continuing our exploration of the OEIS, the Online Encyclopedia of Integer Sequences. And today, we're diving into a sequence that's maybe a little abstract at first glance, but stick with us. This one's A000090.
Yeah, it's a fun one. This sequence actually takes us into the world of permutations, but with a really interesting twist.
So permutations. I'm listening.
So imagine like you're shuffling a deck of cards.
Yeah.
Every time you shuffle, you're creating a new arrangement, a permutation of those cards. Now imagine you're only allowed to swap cards in groups of 2, never 3.
Okay, so no like 3-card Monty moves allowed.
Exactly. And that's where A000090 comes in. It counts the number of permutations that follow that rule, the no swapping in groups of 3. Mathematicians call these 3-card swaps 3 cycles.
3 cycles. So A000009 is all about avoiding those 3 cycles.
Precisely.
Yeah.
And the fascinating thing is, as the number of items we're shuffling increases the number of these special permutations, the ones without the 3 cycles, they grow in a very specific way. Like with just 3 items, there are only 4 permutations that avoid 3 cycles. But if we bump it up to 4 items, that number jumps to 16.
Wow, that's a pretty big leap. It's like there's some hidden force driving that growth.
Yeah.
Is there a way to kind of predict how many of these special permutations we'll have as we shuffle more and more items?
There is, and that's where the math gets even more interesting. Mathematicians have figured out a formula to calculate it, and it actually involves the mathematical constant E, E from calculus, right?
Oh, yeah.
E, that's the one that's always associated with the continuous growth, bacteria multiplying or something like that. But shuffling cards, that's not continuous, is it? That's like, what, discrete?
Yeah, you're exactly right. It seems counterintuitive that E would pop up in the world of shuffling, which is all about these distinct separate steps.
Right, so how does that even work? That's a great question, and it really highlights how unexpected this sequence is. So as the number of items we're shuffling gets really, really large, that number of permutations without 3 cycles, well, it starts to behave almost exactly like a function that involves E. It's like somehow the continuous world and the discrete world of shuffling are kind of intertwined.
That is wild. So it's like this sequence A000000 Nello, it's almost like a bridge between these different areas of math.
Exactly. And there's even more to it. A000009 also has something called an exponential generating function. It's like a special formula that basically encapsulates all the information about the sequence in one neat package.
Oh, wow. So it's not just a random list of numbers. It's like a code almost.
Yeah, exactly like a code. And that code is full of these beautiful mathematical patterns and potentially even some really interesting practical applications. But we'll save that for later.
Okay. So now that we've kind of got a handle on what A000090 is, I'm really curious to see how all this connects to other parts of math. Like, where do we go from here?
Well, there's a whole lot more to explore. We can delve into its asymptotic behavior, how the sequence acts as we shuffle more and more items. And there are even connections to some other really cool sequences in the OEIS, but we'll dive into all that in our next segment.
Okay, so we've been talking about how A000090 counts these special permutations, the ones that avoid those 3 cycles. And it sounds like there's way more to this sequence than meets the eye. You mentioned asymptotic behavior earlier. What exactly does that mean?
So asymptotic behavior basically describes how a sequence acts as its input gets really, really big. Like we keep increasing it towards infinity.
Oh, okay. So in this case, instead of shuffling like a regular deck of 52 cards, we're imagining shuffling like 1 billion cards or something.
Exactly. As that number of items n grows towards infinity, the number of permutations that don't have those 3 cycles, the ones A000090 counts. Well, it starts behaving like a very specific function. It's almost like this predictable explosion of possibilities.
Interesting. And this predictable explosion is connected to that constant E somehow.
Right. The asymptotic behavior of A000009 actually involves a term with E raised to a certain power. It's pretty wild considering that E usually shows up in like continuous math stuff, like calculus.
I know, right? It's so strange how this rule about avoiding 3 cycles when you're shuffling leads to all these unexpected connections. You also mentioned before that A000000 is linked to other sequences in the OEIS. Could you give us like an example?
Sure, one sequence that's connected is A00000142. This one counts what are called derangements.
Derangements. Okay, now that sounds like something out of like a mystery novel. What is a derangement?
Yeah, it's got a kind of dramatic name. Basically, a derangement is a permutation where none of the objects end up back in their original spot. Like, imagine you're sending letters to your friends, one to each of them, but you accidentally put every single letter in the wrong envelope. That's a derangement.
Oh, wow, I've definitely done that before. So how does this connect back to A000090? our sequence about the 3 cycles?
Well, it turns out that the number of derangements is super closely related to the number of permutations that don't have any 3 cycles. Like, the formulas for both of these sequences, they share some really striking similarities, almost like they're two sides of the same mathematical coin.
So even though we started with this pretty simple idea of shuffling and avoiding certain swaps, we've ended up with this web of connections to other math concepts that seem totally different.
Exactly. It really shows how interconnected math can be. And that's just one example. O00000000 is actually linked to several other sequences in the OEIS, each one offering a new perspective on this fascinating little corner of the math world.
Wow, this deep dive has really shown me just how much depth there is to this sequence. We've gone from shuffling cards to derangements to the constant E. And the crazy thing is we've only just scratched the surface.
Wow.
And it really does feel like we've stumbled onto this like hidden treasure map, and every time we find a clue, it just leads to something even more exciting. But before we totally wrap up our exploration of A00000000, is there anything else about this sequence that really jumps out at you?
You know what I find most fascinating? Is that even with all these crazy mathematical connections we found, the sources we looked at, they don't really mention any direct real-world applications for A000090.
Wait, so you're saying this sequence, out of all of them, might have some kind of secret use that we haven't discovered yet?
Well, it's definitely possible. I mean, history is full of examples where abstract math ideas eventually found really surprising practical uses. Like, think about number theory. It used to be considered totally theoretical, but now it's like the backbone of modern cryptography.
Yeah, that's true. So maybe A000090 is just waiting for its big break. Like, who knows? Maybe it could be applied to problems in computer science or cryptography, or even in understanding like complex systems in nature.
Yeah, exactly. I mean, that's a challenge for all of you listening out there. Maybe one of you will be the one to discover a real-world connection for A000090. After all, the true beauty of math isn't just in how elegant it is, but also in its power to help us understand the world around us.
That's a great point. It's like we're sending our listeners off on this mathematical treasure hunt. Who knows what they'll find out there?
Exactly. And with that thought, we come to the end of our deep dive into A000000. We hope you keep exploring and stay curious, and keep those calculators handy.
Thanks for joining us on this incredible journey through the world of integer sequences. We'll see you next time for another deep dive. Until then, happy exploring, everyone.